In the last lecture, we talked about the realization of differentiator, and in this lecture, let us talk about FM discriminators. Okay, so we said you have an FM signal, and this FM signal is given to two band pass filters. Let's say band pass filter 1, the same signal is given to band pass filter 2 also. Okay, and this one is given to envelope detector 1, then this one is given to envelope detector 2, and you take the output and this one like this. Now the question that is in front of us is, how do we realize this in practice? Okay, well, we can realize it exactly the way I have shown it. Like you take the FM signal and give it to two band pass filters followed by envelope detector, and then finally put the summation. Okay, now if we realize like this in this figure shown, what you like to do is you have to have some kind of circuit which takes the difference between the two output amplitudes. So here you are getting one amplitude, let's say E1 of t, and here you are getting E2 of t. You have to take the summation of these two. Okay, now the question is, how can we do that? Okay, how can you combine E1 of t and E2 of t? So for that we can use a difference amplifier or something like that. Okay, the techniques for combining the envelope detector outputs is you can combine them by using a difference amplifier. So you have two outputs, one is from envelope detector 1 and the second one is envelope detector 2. You can combine these two guys using difference amplifier. But there is a more popular passive alternative circuit than your difference amplifier. Passive alternate circuit. Instead of using the difference amplifier, simply you can use resistance and capacitance, and you can build the difference amplifier. Okay, and this passive alternate circuit realizes this kind of operation in one go, and not needed a difference amplifier. Okay, so techniques for combining envelope detector outputs. Okay, so you can use a difference amplifier or you can use a passive circuits. Okay, so now let us talk about the FM discriminator. So based on this argument, some kind of circuit which will work as an FM discriminator. So the input modulated signal is coming in, and through a suitable use center tapped transformer, and it is fed to two circuits which are operating in parallel. Okay, so you take a center tapped transformer, you apply your modulated signal here, FM modulated signal or PM modulated signal. So let's say in general angle modulated signal, and then you take a center point. In between you have two more inductors, L and C, and here also identical inductors, not identical, two more inductors and capacitors, and finally this is my envelope detector, diode followed by resistor and capacitor. And here also you put a diode and then put a resistor, a capacitor. Let's say this terminal is A and this one is B for reference to talk about that. Let me call this is D1, D2, and this point let me call A, point B, and then point C, like this. Okay, let me say I and I dash input. Okay, that's it. This is my circuit diagram. Now let us see how the circuit works. So the input modulated signal is given to the primary of the transformer. Okay, and we are using a center tapped transformer here. This is a RF transformer. The transformer works at radio frequency. Normally whatever we are using in the laboratory for power supply, that works at 50 Hertz, but this transformer works at a high frequency, so it is a RF transformer. And the output of the center fed transformer, center tapped transformer, is given to two circuits which are operating in parallel. One circuit is this one and another one is this one. Two circuits. Okay, each of them has a band pass filter. Let me say this is band pass filter 1. Your parallel combination of L and C act as a band pass filter. And here also the parallel combination of L and C, again this act as a band pass filter. But of course their center frequency is different, that we discussed in the last lecture. Okay, so I am representing it approximately by a parallel LC circuit, right? The band pass filter is represented or designed by using parallel combination of L and C. So this can be more elaborated than as a simple parallel LC circuit, but this is the most common way of denoting it, band pass filter. And this is followed by an envelope detector. Recall from your envelope detector, you have simple diode followed by resistance and capacitor. Recall the circuit diagram. Same circuit is here: capacitor, resistor, and diode. So this is my envelope detector 1 and this guy is envelope detector 2. Okay, so I have two envelope detectors. If you remember, the envelope detector contains, as I said, a diode followed by R and C, RC circuits in parallel. So at any given time instant, okay, it has both positive envelope and negative envelope. This one, the upper guy gives positive envelope and the lower guy gives the negative envelope. And the input is the angle modulated signal. Okay, so at any given time instant, the polarity will be like, let's say this is plus and if this is minus, and again this point is plus and this point is minus. Okay, whatever I have in the upper branch, this one, the same similar circuit I have in the lower branch. Of course, the values are different, especially in the band pass filter. So all I do is I simply combine the lower and upper branch, like this. So this is one combination dotted in the red color line, and similarly the upper branch also I can combine like this. So in the upper branch I have band pass filter, let's say 1 followed by envelope detector 1. Similarly in the lower branch I have band pass filter 2 followed by envelope detector 2. Same signal is given to both the upper guy and the lower guy, and add this like that. So as you can see, the output between the terminal A and B, okay, so the upper point and the lower point proportional to the positive envelope coming at between A and B. Let me say this point is B and I am sorry, this point is C. So whatever you are looking at, small a and b, the point small a and small b is proportional to the value which is coming between the capital A and B. because at any given time either diode D1 conducts or D2 conducts. Okay, when diode D1 conducts in the positive half cycle, okay, and at that time diode D2 will conduct in the negative half cycles with respect to the input. Okay, of course it has to be positive cycle for the diode D2. So positive half cycle of the diode D2 will be the negative half cycle of the diode D1. So essentially the top circuits will be sensitive to the positive envelope and the bottom circuit will be sensitive to the negative envelope. And if you add them two outputs, effectively you would have subtracted what you want to do. So you have carried out the subtraction that you really wanted to carry out, because you are adding positive thing with the corresponding negative thing. Okay, of course the two envelopes are symmetrical. You are assuming two envelopes after the band pass filter and okay, after the band pass filtering. So in the input side you are applying frequency modulator signal that is coming in. Let me say this is L1, C1, L2, C2. Okay, so now let me delete these circles so that okay, this is A. Now let me denote this point as I, and this one is K, then this point is J, just for giving the explanation. So at these points like I, K and K and J, you have two amplitude modulated signals, right? So recall from the previous lecture, after the band pass filtering you have the modulated signal. Okay, two amplitude modulated signals. So the output of your band pass filter is nothing but two amplitude modulated signal. Why is it amplitude modulated signal? Because band pass filter will act as the differentiator. So you have cos omega ct plus phi of t. If you differentiate that, then you will get minus of omega c plus phi of t times sin omega ct. Now as I said, this is the amplitude modulated signal. Why is it amplitude modulated signal? You can think this omega c is some constant and this phi of t is proportional to d by dt of m of t. So this I already explained. Therefore your output of your band pass filter, input is frequency signal, output of your band pass filter is an AM signal. Once you have an AM signal, then give it to the envelope detector. That's what it is happening here. So between I and K I have amplitude modulated signal. Between K and J I have another amplitude modulated signal. Therefore I have two amplitude modulated signals here. When this diode D1 is positive to the positive envelope and okay, so in that case this diode D1 is positive and diode D2 will be negative. Okay, therefore positive envelope will come from the diode D1 and the negative envelope will come from the diode D2, because the two AM signals are identical and therefore you simply add the two outputs. Therefore you are able to produce the output. Let's say the upper one produces the output E plus of t and the lower one is producing E minus of t, E1 plus of t, E2 minus of t. So your detector output YD of t is going to be E1 plus of t minus E2 plus of t. This point is positive and this point is negative. For the lower envelope detector, this point is positive and this point is negative. I'm sorry, the other way around. Positive and negative. Okay, these two LC circuit L1 and C1 are tuned to the center frequency of C1 and L2 and C2 is centered to the tuned to the another center frequency F2. And these two frequencies lies are the boundary of your carrier frequency. Like if you recall the figure, then you have some kind of S kind of shape curve. So this is your carrier frequency, this is the tuned frequency of your let's say filter 1, and this was center frequency of the another filter, and this S curve we got from the 2 band pass filters like this. Recall those things from the previous lecture. Okay, because the two envelopes are slightly looking at through the diode slightly different, I mean the envelopes that you are looking at through the diode detector are different, because you have different tuned circuits. One envelope, one L1 and C1 is tuned to one frequency, let's say F1, and L2 and C2 is tuned to another frequency F2. Okay, so the upper band pass filter is tuned to frequency F1 and the lower band pass filter is tuned to frequency F2. Therefore, the responses are different. Okay, that's the whole point. So this E1 plus of t and this E2 minus of t, okay, so are added at the output. The envelopes are different because two band pass filters are different. So what you get is E1 plus of t minus E2 minus of t. So in other words, let me just restate the argument that output of your upper envelope detector is proportional to the magnitude of the band pass filter. Okay, so let me say my band pass filter 1 has response H1 of f, right? Therefore, the envelope detector 1, this output is proportional to magnitude of the band pass filter, because envelope detector basically traces out the magnitude, right? It captures the trace of the signal, that means magnitude. Therefore, it is proportional to magnitude of the band pass filter, that is H1 of f, where H1 of f is the frequency response of this L1 and C1, this circuit L1 and C1. Similarly, the output of the lower envelope detector will be proportional to magnitude of band pass filter 2. Its frequency response is H2 of f, and this one is given to envelope detector 2, and this output is proportional to H2 of f. Therefore, your envelope detector output or demodulator output is proportional to H1 of f minus H2 of f. So this is what you wanted to do. Again, the question that we raised some time ago is, can't we first do the subtraction and then envelope detection? Okay, so you cannot do that. So the answer is no. The answer to this question is no. So this is what you wanted to do. You don't want the envelope of H1 of f minus envelope of H2 of f. So what we want is, we wanted to subtract the magnitude of H1 of f minus the magnitude of H2 of f. Okay, we would like to subtract the magnitude, not the signal itself. Okay, we want the two magnitudes to be subtracted from each other. Magnitude of the frequency response of the filter. Envelope is different. Okay, so envelope denotes the signal, and here what we are saying is magnitude of the filter response. Let me put a magnitude here. That's it. So that is important point to appreciate. Okay, so such a device that I have just indicated in the above figure is known as balanced discriminator, because the lower one is balanced with the upper one. Balanced discriminator. So this is also called a balanced discriminator. Basically, the term balanced is used to indicate that the response to the carrier is balanced out. Okay, and therefore the final output due to the carrier frequency itself is 0. So if you take a response like this, I'm sorry, like this is my carrier frequency, and this one is, let's say, F2, and this one is F1. According to our frequency modulation, at carrier frequency my output should be 0. If you take only one band pass filter, then the output will not be 0. But if you take two band pass filters, BP F1, band pass filter F2, then at this point it will cancel each other, balanced out. That's what we mean by balanced out discriminator. So therefore the non-zero value becomes 0 value because of these two band pass filters. Okay, so the carrier is balanced out. When I say balanced discriminator, what do I mean? The carrier is balanced out, and therefore the final output due to the carrier frequency itself is 0. So I have two circuits, band pass filter 1 and band pass filter 2, okay, which have identical response at the carrier frequency. See, in this portion the response is different. Okay, here the response is something different, and here this response is here, and this response, maybe you use a different color. If you look at here, this is my response and this is my response. So the response is different from band pass filter 1 and band pass filter 2, but exactly at carrier frequency both the filter gives the same response. Okay, so band pass filter 1 and band pass filter 2 will have identical response at the carrier frequency. Therefore the final detector output due to the carrier frequency will be 0, because you are taking the difference of these two band pass filters output. So in that case, at the carrier frequency the response is identical. So if you subtract, what will happen? The output will become 0. Okay, when the input signal is at the carrier frequency, then the output will be at that instant 0, because two circuits will behave identically at that time. So that is the balanced discriminator. Now you can look at in the literature and in the textbook, you can find out many variations. So there are several variations of this theme, and there are number of variations of this practical implementation. How do you implement and on what basis? There are many variations, and which you prove these implementations can improve upon this using basic principle. Okay, so maybe I list out some discriminators, something called phase shift discriminator, like a balanced discriminator we have phase shift discriminator, then ratio discriminator or ratio detector, and another one is faster Seeley FM discriminator. So you can read on your own. Okay, find out a suitable book and you can read on these things. Okay, not all of them are discussed in a single textbook. Okay. So till now we have discussed the entire theory of your frequency discriminator in a formal fitting by considering precisely how the discriminator works. Okay, so we have developed a model for the discriminator, theoretical models, and then looking at the output of this model. Now let us look at the mathematical theory for this slope detection. Okay, so maybe I will talk about this in the next lecture. Let me stop at this point. Okay, so in the next lecture we will talk about the mathematical theory of your slope detection, how the slope is detected. Basically that's what we have discussed so far. So mathematically we will see that. So developing mathematical theory we will work with a slightly idealized filter. So whenever we develop a mathematical model, we will assume that ideal conditions. So using ideal conditions, let us describe the mathematical theory. Basically, to elaborate further as to what I mean by this idealization in the two bandpass filters, right? We had a two bandpass filter 1 and bandpass filter 2. For this, let us develop the mathematical theory. Conceptually, we have discussed it now. Let us look at quantitatively. Okay, so we are really using only the linear portion of your bandpass filter. So the linear portion only we are interested in. Okay, in the linear region, we are trying to utilize and get back our message signal from the amplitude modulator, from the frequency modulated signal. Okay, so that we will discuss in the next lecture. Let me stop here. Even I can discuss now itself, but if I include that also, then the length of the lecture will be more. So that is why I am stopping at this point. Okay, so I'll continue from this point onwards in the next lecture, so that it is easy for me to upload in the YouTube. Okay, thank you very much.